Okay, good morning. Hi, 11 o'clock. My name is Jim Pascoe. Today I'm going to be talking to you about how to use C++20 coroutines for networking. So just a few bits of housekeeping before we begin. So these are my URLs, so if you want to find out a bit more about me, have a look at my website. The slides are actually online, so you can do basically what I'm doing from the podium. If you go to this URL here, so James Pascoe, GitHub.io, ACCU 2022, so it might make it a bit easier to see some of the code examples from the back, possibly. There are a couple of little videos that are in here as well, so it might make it easier to just read some of the sort of smaller fonts. All of the example code is on my GitHub, so that's at that URL there. If you do want to drive it from your own browser, you can click the hamburger. If I do that on the right screen, and you can hop around the presentation. You can change themes if you prefer a light theme rather than a dark theme. Okay, all right, great. So I thought I'd start the presentation with a poll. So how familiar are you with coroutines? So put your hands up if you are. So far not. There you go, right. Put your hands up if you consider yourself to be a coroutine expert. Oh, that's good. Oh, okay, John, all right, okay. No, I'm really quite scared about question time now. All right, put your hands up if you've got a strong grasp, or you think you have a strong grasp. Okay, brilliant. Guy, I can see, yeah, keep on. Brilliant, need to fill in some details. What about if you have some understanding, but you want to learn a bit more? Okay, yeah, all right. Well, probably, I'm somewhere between 2 and 3, I'll be perfectly honest with you. Or number 4, you're just starting to learn about them. Okay, all right. So for those of you that put your hands up at some point, put your hands up if you thought the learning curve to learning C++20 coroutines was a bit steep or a bit tricky. So when you sort of came to it, you know, possibly after things like concepts and stuff. Anyway, okay, this talk is for you. So what I want to do is I want to demystify using C++20 coroutines for networking. So if your goal basically is to sort of understand and learn about what's in C++20 for coroutines, particularly in the context of networking, then that's really, you know, that's the objective of my talk. The emphasis is going to be very much on sort of practical examples in code. So what I like to do with presentations is I like to make sure that the code examples that I give you are complete and that you can download and even cut and paste off the slides, compile very easily just with, you know, tools that are probably on your laptops now, and actually run them and actually sort of, you know, try and get into some of the details and actually sort of, you know, kind of catalyze your learning process a little bit. We're going to talk about coroutines, the fundamentals, their benefits, their usage. And I'm going to do this in 2 ways as well. So not just C++20, but those of you that sort of know me know that I'm a fan of Lua. So I'm going to talk about coroutines in the context of Lua a little bit, and then obviously in C++20. Then we're going to get into the details of how to actually write networking code using coroutines. I've got quite a few examples on that. We're going to look at how to write a chat program. Quite like chat programs because they tend to sort of fit well into talks. And they're sort of examples that you can understand quite easily on slides, but at the same time, they're not, you know, sort of trivial, and they're not, they're not super complex either. Going to talk a lot about Boost.Asio. So Boost.Asio 178, which is the most recent version of ASIO, has what I would consider to be sort of fairly mature support for C++20 coroutines. And if you've not come across ASIO before, thoroughly recommend that. It's an extremely good piece of code. And not only would it sort of teach you about networking in general, but also asynchronous programming. So really good. Just out of curiosity, who's worked with ASIO here? Yeah, most of you. Okay, all right, that's great, that's great. Then we're going to briefly finish up with a little bit of coverage about the future of coroutines. And so we're going to talk briefly about C++23 and 26. Okay, all right. So a few notes. The example code. It's all built with GCC 11.2. Reason for that was because it seemed to have the sort of easiest out-of-the-box coroutines facilities, so I use that. Like I said, Boost.Asio, I know all these examples work with 178, which is the most recent version. Also works with 176, reason I mention that is because if you're on a Mac and you do brew install Boost, I think at the moment in the seller you get version 176, which is also fine. The Lua examples all run with Lua 544, which is the most recent version of Lua. Who here has used Lua, just out of curiosity? Yeah, great. All right, quite a few of you. Again, really worth having a look at, lua.org. It's got a really nice, really small, simple, compact, very embeddable runtime. Highly recommend having a look at that. And the community is very nice as well. So if you want to ask questions and so forth, lovely group of people. Examples require Lua POSIX and Lua Socket, which are libraries that come with Lua. To install those, just use Lua Rocks. Simple matter of Lua Rocks install Lua POSIX, Lua Rocks install Lua Socket. Tested all this on Linux and Mac OS X. I know it runs on Mojave Big Sur, not that there's much difference in this regard. And obviously it runs on Mint as well. Haven't done much with Windows. So if anybody does try this on Windows, that would be very interesting. Okay. Fundamentals. All right, so now I get into the details. Coroutines. All right, now, when I'm thinking about coroutines, I do quite like the term subroutines. So I tend to think of coroutines as subroutines. Subroutines can be functions, or they can be coroutines. But they're sort of functions with a difference, if you like. They have enhanced semantics. So this is the whole point. So the key benefit of a coroutine really is its suspension and resumption semantics. So with a function, you can obviously call a function and the function can return. But with a coroutine, you can call a coroutine, it can return, but you can suspend it in the middle and then you can resume from that point later. And that really is the, the sort of the real nugget, that's the real piece of gold. So coroutine is initially called for a caller. Like I said, you can suspend execution, which point control gets returned to the caller, and then later on, the coroutine is typically resumed after an asynchronous event or some computation or something. So, like I said, invoke by caller, they return to caller, you can suspend execution, you can resume it. Right, benefits. Okay, right, so why have these? What do they do for us? Well, if you look at the Boost website, so if you look at ACCU in particular, it has a very nice piece of documentation called C++20 coroutine support. So there's a page in the ACCU docs where it goes through the coroutine support. And, Chris Koloff's done an amazing job. I mean, it's really very good. But he starts off with this sentence. So he says, the benefit of coroutines is that you can write asynchronous code with the readability of synchronous code. And when I first sort of, come across this, and there are other sort of sentences that are equally as kind of like, equally as sort of short and pithy. It feels quite nebulous to me, or on first reading, and I'm somebody who thinks I know what a coroutine is. But we're going to get into this in a minute. So what I'm going to do is I'm going to supply some examples, which is going to show exactly what this kind of statement means, and gives you some idea of actually, where this comes from. Coroutine is very useful for networking. It tends to be the case that we have lots of blocking operations in networking. So if you think back to the 90s, or even if you think back to, sort of just blocking programming, connect, sends, receives, there's, sort of thousands and thousands of cycles, if not, kind of millions of cycles between a connect happening and then a send and a receive. So obviously, if your process is blocking, or your thread is blocking for that entire duration, then you're missing a trick because that latency window you could be doing useful work in. Okay, so as I say, ways to sort of mitigate this. Well, you could start throwing in some multi-threading. Yes, and obviously that happens on servers. You have an awful lot of it. And then, you end up with sort of asynchronous operations, which mean callbacks. And very quickly what happens is, the sort of the control flow fragments, and you end up with this kind of callback swamp that becomes very difficult to sort of understand. So like I said, what we're going to do now is we're going to go through an example, and this example is an echo server. And what an echo server does is basically it's a piece of, it's a TCP server that you can connect to. You send it a string, and it sends you back a string. So what I'm going to do is I'm going to show you this little video. So the idea is that, you can take this away, watch this, pause it, and then, sort of run exactly the same things that I've been doing. So obviously this is me downloading my own code. So I'm running G++11. You can see my Boost compilation line, or rather the compilation line including Boost. So I'm going to build the blocking version like that. Then I'm going to go back. I'm going to build the asynchronous version like this. Okay, and then the coroutines version, so you can see I'm adding f coroutines minus the C++20. I'm going to say coroutines. Get the coroutine version like that. I'm going to run the blocking server. Then I'm going to go into another tab, and I'm going to say hello world, and then I'm going to talk to myself. So that's basically what the server does. And then just to show that there's no sort of smoke and mirrors, I'm going to do the async version as well. So you get the idea. I think you can connect to it. And here's the coroutine version, and you can see it all does exactly the same thing. So functionally, these three programs are equivalent. Okay, and like I said, so you can use that, and just pause the video and basically run the same commands at the same time. So, okay, right, let's have a look at some code. All right, so this is the blocking server. So I'm going to, if I look at this, so this is a 40-line program, so it's very readable. Yeah, I mean, we can just immediately sort of look at this and think, okay, I've got an I/O context, which basically the I/O context, those that are not aware, that contains the state required to sort of run the event loop. So it's like the executor. And we'll get on to executors. That's a very sort of deep and interesting concept. And that's, that's running system calls. So that's work, at the level of sort of select, epoll, other platform-specific calls. If I start looking at this, we're going to call the acceptor. So what this is doing basically is it's saying accept a connection on port 6666 from any interface. So the TCP : v4, where I'm just constructing it empty paren, is basically saying just listen on any interface. And then I'm going to go into this loop. So it's an infinite for loop. I've got a socket. I'm going to wait to accept a connection on my socket. And then I'm going to read some data from the socket. I'm going to check to see if I've had an error. If that happens to be EOF, it means that the client's disconnected. No error, I'm going to write it back. Then I'm going to go around the loop again. If the client has disconnected, I'm going to break out of the loop. I'm going to destruct my socket, which is going to close it through RAII for me. And I'm going to go around the loop again, create a new socket, and wait to accept a connection. All right? So very, very simple, very, very straightforward. Okay. Let's have a look at the asynchronous version. All right? So, I mean, I certainly remember writing code like the blocking version back in the 90s. So like 96, I can remember, that was how socket programming sort of basically looked. Right? And then people became very aware that actually quite a lot of performance was, being lost because, like I say, you have these long windows between accepting a connection and sending any data where you could be doing useful work, but you're not, because the whole process at that time is blocked on the, on the first call, basically. So along came asynchronous programming. So asynchronous programming basically means callbacks. Now, okay, so here's a piece of code. Now we can immediately see, just me scrolling through it, it's a lot more complicated, feels a lot more complicated, and it's about 100 lines long. So it's about double the length. And like I said, immediately there's a lot more complexity. Now, I have been a little bit, I could have made this a lot tidier, to be fair. I'm trying to just make the point, basically. And in fact, if you look at Chris Koloff's example for Boost, he does it with a class, which is much better because quite a lot of the wrapping lambdas disappear. But anyway, okay, so the basic principles have changed now. So whereas with the blocking server, we're basically going through a list of sequential steps. So we're saying we're going to connect, we're going to accept a connection, like this. What's happening here is we've got the same sort of preamble. So we're going to create a socket, we're going to accept a connection. But then what we're doing is we're setting up effectively a cascade of callbacks. So I'm going to say, okay, here's an asynchronous accept. At some point, that's going to call accept handler. And then from accept handler, we're going to tee up the next operation, which is going to tee up the next operation. And we're going to go around in a loop like that. Okay, so here's the main code. And then, like I said, first, after the sort of preamble, I'm going to call async accept. So that function is going to return immediately, and it's going to say, at some point in the future, when you do an acceptance, call my acceptance handler. Then the main thread is going to run the context, right? The I/O context. Now, as I said, in Boost.Asio, an I/O context is basically an executor. So an executor says what gets executed, when, and on what, basically. And it's, as I said, there's a little bit of depth to that, which we'll come to later. Okay, then at some point in the future, we call accept handler, all right? And then the first thing we do is check for an error. If we've got no error, which is the normal case, we're going to say, okay, great, that's fine. Let's tee up a read. So I'm going to call it async read sum. So that function is going to return immediately, but it's registered a read handler for me on the I/O context. So at some point, that's going to fire. And indeed it does. So we get here. Okay, so at some point, we've read some data from the socket. If there's no error, we're going to schedule a write. If there is an error, chances are, the likely case is that it's probably EOF, okay, which means that the client's disconnected, right? So in which case you want to close the socket, and we're going to tee up an accept again, okay, because we want to go back to the beginning. So we want to basically make the server available again for connections. So we want to, kind of, if you like, reprime the machinery. And at some point, I kind of said that. And at some point, our right handler gets called. In which case, that's brilliant. We've finished the write. We've done the echo. So now we're going to tee up the read again because we want to, for the normal case, we want to spin around that until the client disconnects. All right. So that's a blocking server. Okay. So now let's look at the coroutine version. Okay. All right. So how much code have we got here? Ooh, well, that's much better. So immediately, this is 50 lines long. And immediately, you're looking at this, and certainly to my eyes, this is far more readable than the kind of the asynchronous code. So certainly, if you imagine, this is a very small example. So if you imagine an asynchronous server with a lot more asynchrony and some multi-threading and stuff going on, you can see the complexity. But immediately we can see, okay, we've got the same preamble. So we've got our I/O context, we've got our socket, we're going to call our acceptor, then we're calling this interesting function co-spawn. What does that do? Okay, so co-spawn is an ASIO function that spawns a new coroutine-based thread of execution. So the Boost.Asio docs term it strand. As I understand it, co-spawn doesn't actually create a thread as such. It uses the threads that are in the thread pool from I/O context. Also, this interesting sort of detached keyword here is, well, it's not a keyword, it's a completion token. It says basically there's no completion handler waiting for this operations result. So it's another way of saying, actually, I don't want to fire a handler in this case. So, all right. So obviously the context runs, the rest nothing happens. Now, okay, so this is actually the coroutine. How do I know it's a coroutine? Okay, it's because I can see I'm calling co-await here. So I immediately know that this is coroutine. That also means that basically I've mandated that in my return type I will do certain things, right? Because the one thing that you realize quite quickly when you start getting into coroutines is that it's very much a sort of a joint operation between the compiler and the code. So you have to supply certain types, which we'll get into in a minute. So here's my coroutine, echo. So the first thing it's going to do is this line here. So it's going to call co-await. And it's co-awaiting on async accept. So what co-await does, basically, is it suspends the coroutine until that event happens. So in effect, basically, what we're going to do is we're going to suspend at this point, and we're going to say, right, resume me when this event actually happens, right? So what actually happens when co-await gets called? Well, basically three things. So all the local variables for the coroutine get saved into a heap-allocated coroutine frame, okay? And then secondly, a callable is created, which, basically when it's invoked will bring me back to this point here and through a chain of code that we'll go into. So that callable is called a coroutine handle. And then thirdly, what happens is execution jumps into a method of something called an awaiter, all right, which we'll get into in a minute. And it's this method, which is actually called await suspend, which schedules the resumption of the coroutine. Okay? So the coroutine is suspended from that point, and control returns to the executor, right, which is in co-spawn. Okay? All right, so at this point, okay, so the coroutine is, the executor is waiting for events. It's going to spin round. Eventually, we get an acceptance. Once that happens, we're going to go to here, and we're going to co-await on async read sum. So again, similar idea. We're going to suspend the coroutine until we've read some data, basically, until the executor has said there's some data that you've now read. Similar idea with the error checking, and then basically we're going to do the same with the writes. Yeah. So we're going to suspend the coroutine, and we're going to wait until the write is completed. Now, whilst the coroutines are suspended, right, other coroutines can run. Okay. So this latency windows that are, sort of here with async accept, the async read sum and async write are now, totally sort of up for grabs for other coroutines to be scheduled in and to do useful work. And that's, that's the benefit here, right? Okay, all right, good. Okay. That was a sort of simple example. Basically, the idea was to sort of show you the kind of the benefits of coroutines. Has anybody got any questions at that stage? No? Okay, great. All right, so let's get into the details. Coroutine support in C++20. Okay, what do we actually get in C++20? Well, we get 3 new keywords. So that's co-await, co-yield, co-return. And for me, really, the star of the show is co-await, because that's, as I say, that's what's doing the suspension of the coroutine, and that's what's returning control to the caller. So co-yield is very useful for what it does is it yields values from a coroutine and then suspends. So if you think of a generator, I mean, like, I'm guessing that probably everybody's seen an example of a generator in terms of C++20 coroutines. Co-yield basically produces a value and then it suspends to the next iteration. So it kind of like, it sort of turns the handle. You get a value out and then it resets the machinery ready for the next go. Co-return, it goes one step further. It completes the execution of a coroutine and returns a value. So it basically says, right, whereas co-yield is saying, here's a value and, reset for next time. Co-return is saying, here's a value, that's it, we've returned. We get some new types. Coroutine handle. Like I said, coroutine handles are pointers to coroutine state. They are the primary mechanism used for resuming and, in fact, destroying coroutines. Like I said, coroutine state is actually got, is conceptually quite deep as well. They're usually allocated on the heap, although I think that some compilers are able to actually align that with the caller's stack if the compiler has full visibility of the lifetime of the coroutine. So I think there are optimizations. I don't think it's always the case that it's a heap allocation, but more often than not, and you certainly could not say that it's never the case, that you're not going to do a heap allocation. We get some traits. So the traits are basically there to give you the promise type from a coroutine's return type, and also it's also based on its parameters. And then we have some trivial awaitables, so suspend always and suspend never. And these pop up in a number of places. What they are sort of typically useful for is controlling whether or not we want coroutines to begin in a kind of like an eager fashion or a lazy fashion. So yeah, like I said, so like a generator, probably you want to start it in a lazy fashion. So what that means is you suspend, once you set up the kind of the machinery for the generator, you suspend because chances are there's going to be thousands of cycles between the setup of the coroutine and actually generating the first value. And typically between the usage of those generated values, you want it to, is going to be a long time as well. So. Whereas if you've got something that's going to be computed synchronously, then you might say, well, actually, you know what? I'm just going to create this coroutine in an eager fashion because I know I'm going to need the result. It's synchronous anyway. So I'll start it up and allow that to complete. So, okay. Right, some tips for learning. Like I said, I found, trying to get into sort of C++20 coroutines, the learning curve is very steep. And I think there are a few things that, if you bear in mind, will make that process a lot easier. So it's a little bit about sort of getting into the right mindset. So bear in mind that principally what we've got in C++20, really, I think it's fair to say, is aimed at library development. So it's not really about sort of, user code yet. That's sort of coming. There are libraries with coroutine support. So like I said, ACCU first had support in 1.6.7. That's when it was all quite experimental and so forth. That changed in 1.7.7, which is only fairly recent, really, to C++20 support, and it became sort of quite mature. It's obviously matured over that point, but the documentation changed to C++20 support for coroutines in 1.7.7, and obviously we're on 1.7.8. Lewis Baker and a team of people wrote CPP Coro. This contains a lot of very useful coroutine types, awaitables, all sorts of things that are actually quite useful. Really kind of like the sort of the user code elements that, obviously they're trying to standardize in C++ now. But, they're not quite there yet, but I'd highly recommend having a look at that. And by the way, I'd highly recommend having a look at anything written by Lewis Baker as well. I mean, his insight is really good. Okay, one thing to bear in mind, you'll see a lot of references to things like promises and futures. They've got no relationship to std promise and std future. So I talked to a lot of people about coroutines, and it's remarkable the amount of times people think, get confused by, they see promise, they think std promise, they see future, they think std future. These terms really are being used in the sort of the classic computer science sense. So terms promise and future been around, I think, since about 75. And basically, they've been, a promise is the kind of user-side portion of an asynchronous operation, and the future is the user-side portion of an asynchronous operation, and the promise is the executor side. All right. Okay, so here are some key references. So these are things that I found extremely useful when trying to sort of get into C++20 coroutines. So there's 4 blog posts that Lewis Baker produced. So he's getting a little bit old. These posts, I think, are more sort of 2017, 2018. But if you want to understand what's in C++20, I'd highly recommend looking at these 4. They're quite dense, they're quite tricky, and you have to sort of, kind of fit them together. They're a bit of a puzzle. But these are by far, in my view, the best 4 references. Dave Maziris wrote a very good blog post in February 2021, my tutorial and take on C++20 coroutines. It's very good, quite different to Lewis's sort of approach. And if you really want to understand the details, I would look at the first 4 personally. Gor Nishanov, obviously one of the guys who was there, who invented the support in C++20. If you actually read the WG21 paper for coroutines, it's actually very readable. I think it's only about 16, 20 pages long, and it's it's extremely well written. It's not hugely overloaded in kind of standardese or anything like that. So these are like I said, these key references really to sort of facilitate my understanding. These were the ones that I sort of invested in heavily. All right. So does anybody else want to take a picture of that slide? Or, yeah, we're good. Okay. So we're going to have a coroutine tutorial. So my goal is to implement a chat program using coroutines. So we're going to prototype this in Lua because, I'll show you why in a second. We're going to prototype it in Lua and then write it in C++. And the reason we're going to do it in Lua is because I think this has a very sort of nice way of showing you exactly, what coroutines are in the abstract. I mean, like I said, before we get into the real details of the kind of the C++20 sort of aspects, which, sort of are quite complex and sort of fairly gnarly, I think it really helps to have a very clear understanding of what a coroutine is, how it works, and why it's of benefit, basically. So then we're going to get into all the juicy details. So we're going to talk about co-await, co-yield, co-return. We're going to talk about return objects, promises, awaitables, traits. I'm going to show you an example on generators, and then we're going to actually implement chat in C++ using ACCU. All right, Lua. Okay, so for those of you that don't know, it's a really nice, lightweight, embeddable scripting language. I like it. I like it a lot, but I think it's very useful in this context because it's a good way of sort of building a mental model of coroutines. So if you're at the sort of stage where you're starting to get into coroutines and you don't really have a good sort of understanding of what a coroutine is, I probably wouldn't start with C++20. I'd probably start with Lua, build up some understanding of what a coroutine is, and then apply it to C++20. And if you kind of go that route, then you'll find that what you have is a sort of a framework for your thinking, and then you can decorate that with specific bits of knowledge from from the literature and so forth. So Lua, in this case, is single-threaded, so it means it's all lock-free. There's no races, etc. And this is why I think it's particularly interesting. In Lua, you have to implement your own dispatcher. So the executor, you have to do that. So in the examples I've shown so far, that's kind of hidden away in the I/O context of Boost.Asio. And if you dig into that code, it's complex and there's a lot of sort of detail to it. But actually having a good mental model of what an executor is actually very valuable as well. Lua coroutines are stackful, so broadly speaking, stackful coroutines mean that each coroutine has its own stack. Certainly in the context of Lua, stackful coroutines are called fibers, and they're used in Lua to provide pseudo-concurrency similar to cooperative multi-threading. So by contrast, C++20 coroutines are stackless, and I'd say generally speaking, the world is moving more towards stackless coroutines. There are a number of really good benefits. They're extremely scalable. JavaScript has stackless coroutines. There's also a thing with stackful coroutines where, generally speaking, a yield operation typically means a context switch, and that can be sort of quite heavy. So as I say, by contrast, C++20 coroutines are stackless. They suspend execution by returning to the caller, and the data that is required to resume execution is in the callable stored on a heap, so totally separate from the caller's stack. Okay, so like I said, we're going to write a chat program. So what we're going to do is we're going to have three coroutines, a sender coroutine, which is basically going to read input from the keyboard from the user. It's going to send it to a remote. A receiver coroutine, which is going to print receive messages, and a dispatcher, which is going to schedule the sender and receiver. So dispatcher is the executor in this case. So there'll be a little bit of main code, and like I said, I'll show you the whole program because then you can, I sometimes think it helps to actually see all of the code in context rather than just like, some very, kind of like interesting but, sort of gnarly piece of code. So we'll look at the whole program. Okay, so this is another little screen capture. Like I said, you can follow along with this, but you can see what I'm doing basically. So once again, I'm cloning my own code. So there we go, it comes down into Lua chat. So I'm running Lua. Like I said, I've got Lua 544 installed. I'm running it locally on port 6666, and I'm connecting to 127.0.0.1.7777. And then on the other tab, I'm just basically sort of connecting them together, like RX to TX, if you like. And then I'm having a conversation with myself. So you can see that, I've finished my conversation now. And then I can reconnect as well. So, I want to make sure that the server basically rearms for the next time. So it's telling me not to forget the conference dinner. It's always good. Okay, great. All right, so here is the sender coroutine. So if we look at this, how big is it? About 30 lines. Okay, so it's not massive. What we're going to do is we're going to go into a loop. So like I said, in Lua, coroutines are basically used as a, sort of almost as a proxy for threading, if you like. So you tend to see this is a sort of very common pattern that you'll see. We're going to go to here. So I'm going to create a socket. And I'm going to say, whilst I have not connected to my remote yet, I'm just going to yield the coroutine. There's nothing for me to do. So I'm going to yield back to the executor, back to the dispatcher, let the sender, maybe he's got, work that can be done, but there's nothing for me to do at this point. And then the sender at some point is going to yield, and I'm going to resume on line 9. and then try again and spin around this loop. At some point, I'm going to get a connection. That's great. Let's print out a message. And then I'm going to go into this loop. I'm going to read from standard in. Now, I've got to do this in a sort of non-blocking fashion. I mean, if I was to call the equivalent of getLine at this point, what would happen, do you think? Anybody? It would block, exactly. It would block. It would just sit there, right? So the whole program. So if somebody was busy, sending me messages, right, I wouldn't see them because the whole program is blocked, waiting for the user to input a line of text. I'm going to read from the keyboard. Like I said, I'm going to do it non-blocking, and this is a mechanism in Lua, basically, to do it. But, this piece of code here, what I'm doing is saying I'm going to poll FD0, which is stood in, with a timeout of 1 second. So if the user has not pressed a key in within 1 second, I'm going to carry on. If we have got something, then I'm going to do an IO read. The message is empty. Then I'll just, if the message is not empty, then I'm going to send it. Otherwise, I'm just going to send a null character and carry on. Yeah? And then the moment I come out of this point, if I come down here, basically what it means is that I've timed out from reading the keyboard, so I'm just going to yield. There's nothing for me to do still. Okay. Does that make sense to everybody? Yeah. Okay. All right. Right, here's the receiver. So again, similar sort of length, 35 lines, so not too bad. First thing I'm going to do, I'm going to bind the socket on my port. I'm going to set that socket, again, non-blocking, 100 millisecond timeout. And then I'm going to jump into this loop. I'm going to print out a useful message for the user to say what port I'm waiting on. And then I'm going to run accept. And basically what I'm going to do here is I'm going to say, okay, I'm going to wait for somebody to connect to me. If nobody does, i.e. if I time out, I'm going to yield because there's nothing to do. Otherwise, I'm going to hop into this piece of code here. So I'm going to get the peer name and just print it out. Actually, I don't print it out, do I? And print a banner, set a timeout, and then I'm going to go around this loop which says, okay, receive a line of text. If there's no error, then I'm going to print out what I've received. If there's nothing for me to do, then I'm going to yield, basically. So I'm going to go back to the dispatcher and let somebody else have a go. Okay. So this is the dispatcher. And as I say, this for me is, the first time I did this, it was a light bulb moment as to, sort of how coroutines work, really. Because, at this point, you see the whole story. So you've got the sender, receiver, sender and the receiver, you've got the dispatcher, and you can see the whole thing. That is it. It's 21 lines of code. So it sits on the slide. And you can see basically what this loop is doing is it's saying, okay, if there are no more coroutines, fine, we're finished. We clean the exit. Otherwise, I'm going to spin around my list of coroutines, or table of coroutines, rather, and I'm going to resume whichever one's next. Okay, so that guy gets a chance to execute at this point, gets scheduled onto the processor, gets a chance to do something. If I get a result from my coroutine, it means that the coroutine's finished. So if it's a string, that means it's a runtime error. Otherwise, it's a clean exit. I can print that. And that's it. I spin around that loop. And so the dispatcher or the executor is just basically saying, run the next one. Then that guy has a chance. He yields. And then run the next one and so forth. Yeah? Okay. All right, here's the main code. So like I said, just to sort of give you guys some idea of of everything, basically. This is how you create coroutines, and then, like I said, the main loop becomes the dispatcher at the end. All right, so simple stuff, yeah? So hopefully that gives you kind of like a sort of a model of coroutines and why they're so powerful and what this kind of, this concept of sort of pseudo-concurrency really means, yeah? I mean, basically what you are doing is you are exploiting the sort of the latency windows. You're saying, I know that this operation is going to take a long time, go off and do something more useful. All right, so let's get into the details of coroutines. Okay, so an awaitable type supports the co-await operator. Okay, controls the semantics of an await expression, and I'll tell you what that is. But basically, an await expression is anything that follows co-await. Yeah? Principally, it's telling the compiler how to obtain the awaiter. All right, and the awaiter is the data structure that is, in effect, controlling the suspend and the resume, or the, if you like, the thing that allows us to customize the general machinery. All right, so like I said, when you see code like this, anything following the co-await is an await expression. Okay, all right, so why the distinction? Why do we have awaitable types and awaiters? And the answer is basically, it said there is some subtlety. So, like I said, an awaitable type supports co-await, but whether or not co-await can be applied directly to a type depends on the context in which co-await, the co-await expression appears. So the promise type can actually alter the semantics of the co-await expression through an await transform method, which we'll have a look at in a minute. I've got a slide coming up on that. But by contrast, the awaiter type allows the user to specify the coroutine's behavior at specific points, okay, in the suspension and the resumption process. Right? So, like I said, there is some subtlety. It took me, it's quite, the difference between an awaitable type and an awaiter is really not obvious. And they can be the same thing, and in most cases, it appears that they are. But, as I say, you have this kind of like this capability to do an await transform, which effectively controls the semantics of the await expression. Right? So it allows you to do some very clever things. But like I said, it's not obvious from the literature. Right, let's look at an awaiter type. So what this does is it defines the suspend and resume behavior. Yeah? And in particular, it defines three methods that are very important. So await ready, and this is a method that basically says, do we actually need to suspend the coroutine? I mean, like, if this result is already available, or it's going to be calculated synchronously, do we actually need to go through the suspension process, right? Because suspending a coroutine is obviously, expensive. Right. Await suspend. Okay, when we get to await suspend, we are already suspended. The coroutine is suspended at this point, all right? So the principal job of await suspend is to actually schedule the resume, yeah? So if you dig through Boost and look at ACCU, what you'll find is the await suspend method basically takes the coroutine handle and it attaches it to the operation in the executor. So it sort of wraps it, and then that goes off. And then when the executor fires and says this operation is now completed, then you get the resumption basically. Await resume. Okay, so this is called just before we return to the resume point. All right. So in a coroutine, the resume point, from a user's perspective, is what follows the semicolon from the co-await expression. Yeah. Await resume gets called just before that, and the idea is this is how you interface it to your library's machinery to get the result of the operation, maybe if you need to do anything to present that, and then that result gets returned from the co-await call in the coroutine. Okay. Like I said, this can be the same, you can have an awaiter and an awaitable type, they can be the same thing. And generally speaking, of the examples that I've seen, they are. But like I said, if you really want to understand the absolute sort of the real detailed, there is some subtlety. Have a look at Lewis Baker's post, I think it's the second one, on co-await. He goes into this in great detail. Okay, so the coroutine return type. So I sort of mentioned before when we looked at the coroutine example that actually, you have this class and there is a lot of interaction between the compiler and the coroutine. Yes, that's right. What you have to do, you have to, at the moment, you have to produce this thing. Very often they've got names like task or int, or generator, and you'll see them in various examples. If you dig into them, basically the primary, one of the sort of primary things that they're doing is declaring the promise type to the compiler. So you've got to do that using coroutine traits. And like I said, you'll see in the literature, you'll see examples of this, and they're generally referred to, they've got names like task and generator. So CVP co-row has lots of these, right? And like I said, the idea clearly, certainly at the point of C++20, is to get these, these kind of types into the standard library as well, so that the user doesn't have to write them. That's quite interesting as to where that process has got, which we'll get to in a bit. In some WG21 papers, particularly the early ones, the sort of coroutine return type is referred to as a future. Like I said, I've seen a few people refer to it as the return type. I think it's probably better to call it the return type rather than a future, personally. And like I said, don't get confused with stud future. A lot of people online seem to be doing that. Okay, the promise type. All right, so this is what controls the coroutines behavior. So I think we're long overdue an example. And there's an example of all of this coming up. But basically what happens is the promise type implements the methods that are called at specific points during the execution of the coroutine. Okay? So principally, it conveys coroutine's result or an exception. Again, as I say, don't get it confused with stud promise. A lot of people doing that. Okay, customizing co-await. So I thought I'd include this really for completion, but this is the await transform method. Like I said, you can use it to do some really quite cool things. It's defined in the promise type. It allows you to enable types that are not awaitable. So there's lots of examples. I think there's an example using stud optional, which is quite interesting. Another thing that's very useful is you can disable co-await on certain types. So if you've got a generator, for example, and you want to say, co-await is not defined on this, then you can do that. You can just overload await transform for basically any type and set it equal to delete, and that means you'll get a nice friendly compiler message rather than screenfuls of output. It also allows you to modify the behavior of awaitable values as well. That's getting really subtle. Like I said, if you really want to understand this stuff, have a look at Lewis Baker's blog post. He goes into great detail on it. I haven't really seen, apart from the standard, which also has some detail on this, I haven't really seen any coverage of await transform anywhere else, to be honest. But it's also possible to customize co-yield, although generally speaking, that's far less common. You can do it, again, have a look at the standard or Lewis's blog post for details. All right, coroutine handles. Right, so after all of that, coroutine handles, a bit like a C pointer. They are basically a handle to coroutine frame on the heap. So like I said, the coroutine handles are the primary mechanism through which coroutines are resumed and also destroyed. Okay? They also give you access to the promise type. So I think if you work your way through Dave Mazira's blog post, he goes into, he's got some nice coverage of coroutine handles. But it's also a good way of getting access to the promise type, so you can sort of noodle with fields, via the handle. They are non-owning, so they have to be destroyed explicitly. Very often, that's done through RAII in the coroutine return type. So I'll show you that in a minute. In fact, actually, I should probably show you that now. Okay, here's another example. So here's an example of a generator. So I thought we'd have a slight break from networking examples at this point. And so this is an example of a card dealer. So I don't know if people, I thought maybe after the conference dinner, if suddenly, somebody wants to, start playing cards, you could fire up this program and, and it will deal cards for you. So it's only 80 lines long. Okay, so this is the application. In main, so you can see I'm creating, instantiating dealer. I'm going to give it a deck size of 100. And then I've got a while loop which is saying, right, whilst there are cards, so whilst dealer.next is valid, then give me the next value, print it out. Great. Right, this is the coroutine. So this is potentially something a user would write. Certainly now. So you can see it's a coroutine because I'm using co-yield on line 72. So that immediately mandates to the compiler that I need to supply certain details in the return type of this coroutine. And then if we go through it, so we've got some simple code. So I've got a random number generator, an integer distribution, and I mean, I'm sure you can all see, basically what I'm doing is I'm just picking, ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, jack, queen, king, and then selecting a suit, and then I'm composing a string. So this is the loop. I'm saying, okay, so for each card in the deck, I'm going to yield up basically a string that says, 2 of hearts, 6 of diamonds, ace of spades, this sort of thing. So. Okay, and that would be sort of typically something that the user would write. Okay. All right, so now we're going to get into the generator. So this is as I say, the coroutines return type. This is typically something that, what we'd hope to happen is that in future versions of C++, this would be in a library or even in the standard library. And in fact, I'll give you a hint. I mean, it is coming in the standard library, though I'm not, possibly not in 23. No, exactly. I can see a few members of the committee, and I've got some up-to-date details. Sort of like it's actually it's quite interesting because I've been watching the GitHub paper for the paper of this, right? And whilst we've been at this conference, Bryce Adelstein-Leibach has promoted this from an LEWG paper. So it's gone to LWG. It's been accepted. It was accepted in January in an electronic poll, and it's been accepted. It's gone to LWG for sort of looking at the kind of standard EAST and stuff. So literally, within the last 24 hours, the GitHub's been updated. Anyway, so we still have to write this for now, but that's fine. I mean, it's not a big deal. So what have we got here? So it's actually quite interesting because we can get a handle on some of the machinery. So for declaring the promise type, and I'm saying, here's a type alias called coroutine handle. It looks like that. It's nothing too controversial. Then this is the promise type. So you can see T is the current value. So that is actually the value that we are going to sort of extract from. That's actually going to store the string basically. And then we've got some quite interesting methods. So the first one that gets called. Let me have a look. Yeah, absolutely. So when a coroutine starts executing, does the following, right? It allocates the coroutine frame using operator new, so you get a heap allocation. Then it copies the coroutine's parameters to the frame, constructs the promise object, and then the next thing it does is calls getReturnObject, okay? And then it keeps the result in a local variable in the coroutine. And this is what gets returned to the caller when the coroutine first suspends, okay? So when we're doing all of that setup at the beginning, and this is what gets returned and stored by the coroutine right at the beginning. The next thing that gets called is this, initial suspend. So now you can see the use of suspend always, basically. So this gets called, and then the result is co-awaited, okay? Now, because this is a generator, what I want to do, I want to suspend right from the get-go, right? Because I don't know when I'm going to be called upon to actually produce a result. It could be, in an hour of time or something, right? So there's nothing really for me to sort of calculate at this point. So we're going to return suspend always, and then that gets co-awaited on. So we start up in a suspended state, if you like. All right. So what's next? So by contrast, final suspend gets called just as we're about to destroy, just when the coroutine's finished executing. So when we've fallen off that for loop, right at the end. So we've yielded everything. We said we've got nothing else to do. We've exited. Final suspend gets called. And again, I'm calling suspend always here, right? And there's a very subtle reason for that. And the reason is I want my coroutine to suspend, literally just at the point it's going to be deleted. And the reason for that is because it means that all of this coroutine state stays valid, okay? All right? And that means that I can then call destroy from an RAII type, which is coming up to do the destruction for me, right? If you say suspend never here, you just sort of drop off the end, and then you leak coroutines basically, or you leak coroutine frames. Yield value. This is what gets called every time you co-yield. So you can see, obviously, we're just taking the value, we're just storing it away, and then we're returning suspend always, which is co-awaited upon. So it's kind of like saying, here's the value, it gets stored, and then the machinery just gets reset for next time. Okay. So that's the promise type. So that's embedded in the coroutines return type. There's other things that are here as well. So you can have all of the normal kind of class design, range support. You can see here I've got two functions. So I've got a next function, which is saying, okay, every time that gets called, I'm going to resume my coroutine, so do one iteration, if you like, followed by, so comma operator, not coroutine done. So if the coroutine's not finished, we return true. Otherwise, we return false. Then, what else have I got? And then value, obviously, is just giving me the current value from out of the promise type. Yeah. So now, like I said, because I set the final suspend point to suspend always, right, all of this coroutine state will stay valid. And then the moment that my generator object goes out of scope, then I can say if coroutine.destroy, right? And then that will do the cleanup for me, and that will tidy everything up. Like I said, I haven't seen any examples in the wild of people saying final suspend set to suspend never. It is theoretically possible. I'm not 100% sure why you would do that. But maybe in the maybe if you're into kind of asynchronous joins or things like that, perhaps. But oops. Okay, all right. So, okay, like I said, that was sort of a fun example, car dealership, basically. But a networking example of a generator would obviously be like a traffic generator. So you could imagine the coroutine generates packets, so doing things like sequence numbering, checksums, encryption. And then you could have another coroutine which is actually doing a transmission. So if you wanted to do like a packet generator, which is something in networking I do a lot, you could set it up this way. So basically when you're actually doing the transmission, then in that latency window, you can be setting up the next packet. So like I said, or creating the next packet, so doing, sequence numbers and encryption and stuff. Okay, so let's have a look at a proper example now. So this is a bigger example. So this is chat. So this is going to sort of combine all of these concepts together into a, sort of hopefully non-trivial, but at the same time easy to understand example, basically. Okay, chat, coroutine chat. All right, so we've prototyped it in Lua. Let's write it in C++20. We're going to stick with the same coroutine design. So the sender is going to read the keyboard and send. We're going to have a receiver coroutine that's going to print messages. Dispatcher is, in this case, the Boost.Io context. So that's the executor, if you like. It's got to be non-blocking because, as I say, if there was blocking calls to the keyboard read and stuff, that would stop messages that were coming in from being printed. And users should be able to sort of disconnect and reconnect. Okay, so this is the final one of these. So again, you can see me just cloning the code. So I'm going to build it. So I've got Boost built in my home directory, just because that's convenient. Like this. So coroutine, minus F coroutines minus stud equals C++20. We're also going to use Boost regex for this, and I'll show you why that is in a sec. So we build, and then we run it. So I'm going to run it on my host in two processes. So set up another tab. I'm running it again. So like I said, it's kind of like doing sort of making sure that the RX and the TX are sort of connected together. And then you can see, basically I'm having a conversation with myself. So this one disconnects. He goes back to a state where he's listening, and then you can reconnect as well. So it's not kind of like, it's not a sort of a one-shot thing where you sort of do it once and then it doesn't work again, basically. So. Okay, all right. So, so that was, as I say, if you do want to try this out, you can just go onto the slide, and if you press spacebar, it will pause. Yeah. Okay. So, all right. Let's think about some design then. All right, so we're going to have a chat class. So like I said, if we sort of combine all this into a class, just make life a little bit easier. So I've got some basic code here. I'm going to create a resolver. So what a resolver does is take addresses, typically in a kind of human-readable form, so like strings, and it's going to give me back a list of endpoints, basically. Or in this case, we're only going to look at the first endpoint in the list. So I've been a bit, I've tried to make this as simple as possible, so, there are other ways of doing it, basically. Then we're going to spawn our coroutines. So you'll notice that I'm doing this with the same I/O context, so they're going to be running on the same strand. And that means that any kind of like local data that I want to share can be shared between them. Because it's one thread, they're running on the same thread. Then I don't need any locking, I don't need any mutual exclusion or anything like that. The asynchrony is not, it's, I don't need to guard it. So I'm getting an extra win there, basically. Then I'm going to start running the I/O context. Okay, that's what the main thread's going to do. All right? Okay, all right. Okay, so the sender. All right, now things are getting a bit more interesting. So you could, as I say, you can immediately tell it's a coroutine because you can see co-await dotted around. That means that the return type is significant. So awaitable void is something that's defined in ACCU just for this purpose, basically just to allow you to write sort of coroutines in ACCU. If we start going through the code, so I've got this loop. It all fits onto one slide, pretty much, which is nice. So I've got a remote socket. I'm going to do an asynchronous connect. I'm going to co-await on that. So basically what's going to happen there, obviously we're going to suspend at this point. We're going to go off. And as I say, ACCU will take my coroutine handle. It will attach it to the operation for later. And then it will return back to the executor. All right, so the executor will then be able to run another coroutine at that point. Yeah. Whilst doing all of its system calls and listening to system events and all the rest of it. Then at some point in the future, that event's going to fire, the executor is going to say, yes, okay, there's a coroutine handle here. I need to resume this coroutine. So we're going to go back through the awaiter now. We're going to call await resume, and we're going to come right back to the start of line 8. And we're going to say, if there's no error here, then great, print out a nice message, set a flag. Otherwise, if we're stuck, let's try and reconnect in a second. So again, I can use the boost timers, which are also coroutine enabled, and I can use those to basically wait for a second. So, I've got this sort of steady timer code on lines 15 to 18. Okay, so we get a connection. All right. What are we going to do? Well, first thing we're going to do is read keyboard. Again, this has to be non-blocking. If I call getLine here, then the whole thread will block on getLine because it's a blocking call. So I don't really want to do that. So this is one way of reading the keyboard with a timeout. So I've got a timeout of 100 milliseconds. Obviously, I'm basically saying, okay, poll on FD0, which is stood in. If nothing happens within 100 milliseconds, then fine, we'll do something else. If I do get a hit, then spin around this while loop. Selected. Yeah. Spin around this while loop and read the characters out into a string and then tack on an ending at the end, basically \r, \n. Okay. Then what I'm going to do is I'm going to write it like that. And then I'm going to clear the string for next time. So basically when that write returns. I know that the data's been written out. I'm going to clear the string for next time, and we're going to go around the loop again. Okay, the receiver. All right, so this is the other half. Very similar. So we've got an acceptor, so that's going to sit there waiting to accept a connection. And then we're going to enter this loop. When we did get a connection, we're going to say, okay, I'm going to wait until I actually receive a connection. This as tuple user waitable, by the way. What that's doing is the user waitable is basically telling ACCU to use the overload that produces something that co-await can interpret. So in other words, produces an await expression. The as tuple declaration, so calling it as part of that, means that it gives me back the return values in something that I can use a structured binding on. So I think a stood pair, basically. But I can use a structured binding to extract error in client rather than have to unpack those in other ways. There's also, I would also say, have a look at, there's also a lot of other cool stuff you can do in ACCU because it allows you to do sort of composition of coroutines with double ampersand and double or and things like that. So once we get a connection, we're going to go into here. I'm going to co-await on async read until, and I'm basically going to read data from the socket until I see \r\n, which is the line ending that I put on previously. At which point I'm going to check to see if the remote is disconnected. In which case I'm going to break out of the loop and go around again. Otherwise, I'm just going to print it out as a message. And I'm going to say, yes, here's the remote endpoint, and it sent you this message. And then clear the data, ready for the next time. Okay, so this is just the complete listing. I just scroll through this very briefly. It's just, like I said, you can cut and paste this off the slide. So if you just go here and just do this and cut and paste it into an editor window, you should be able to sort of get this building within, if you've got Boost downloaded, within, basically my target is if you can get it building within sort of half an hour, then, that's the intention basically. But that's the entire program, and it's 134 lines of code. So, should be, sort of, there is some detail, but it should be relatively easy to, sort of like, gives you a bit more context than, like I said, snippets of code or examples that are perhaps quite interesting, but out of context are quite difficult to interpret. Okay, conclusion. Any questions? So I've sort of... Not at this point. Everybody's like desperate for lunch. I can totally understand that. What do you need just before lunch? A really heavy talk on coroutines. Okay, so, right, what's coming in C++ 23.26? I'm really glad that Guy's here and Dietmar's here. There's a few members of the standards committee that I can sort of see dotted around. Okay, so, guys, please correct me if I'm wrong, because like I said, I was literally, sort of updating this yesterday. But so, back when C++ 20 came out, there was a plan. I think if you look at, I think the paper is P1000. The library support coroutines was planned. So the idea was, okay, we've got this excellent machinery. We need to basically provide things like stood generator, stood task, asynchronous, lazily executed tasks. So, basically the user doesn't have to write the stuff that I've been showing you and get into sort of the real details of the promise types and stuff. Now, that whole story sort of evolved. I don't think COVID's really helped with this. I mean, like, Guy, you know better than I do. But so there was a plan to have stood generator that Lewis was working on. So that paper was P2168. That has sort of morphed into P2502, which is standardized generator, which is the same thing. So what I've been talking about with the generator example. Like I said, that was voted on in January, and it got sort of like, strong acceptance. And like I said, literally within the last 24 hours, Bryce has updated the GitHub for this to say that it's now been passed to LWG. So that means that the standard East will be checked. But as I understand it, the kind of code freeze deadline for C++ 23 was February the 7th. So we're sort of beyond that. But I don't know, Guy, do you know, you probably know a lot more about this than I do. But
feature freeze for what would be in C++ 23 was frozen in February. That doesn't mean that everything that was suggested by them will make it through, because it's got to go through library as well. It must meet and say, yeah, the standard is correct. If we can't finish all the standard by next February, which is when we have to build the final draft to balance the whole world and say, is this what we want? Then it goes to the next.
yeah.
So we can't make any guarantees. Obviously, library will work as hard as it possibly can.
Oh, yeah. Yeah, so fingers crossed, but, I mean, yes, but yeah, exactly. I mean, as you say, fingers crossed. But, so, yeah, I mean, like, just to be, I mean, it's amazing, it's sort of having kind of like looked at this a bit. I mean, the amount of work that the committee does is incredible, on top of, kind of real jobs and families and all the rest of it. Absolutely. It's a very good proposal, in my opinion. It models stud ranges, input range. I mean, have a look at it if you're interested. Like I said, accepted by the Library Evolution Working Group, January. It's been sent to Library Working Group. Looks like it's missed C++ 23, but like I said, I got my fingers crossed. I mean, Guy knows a lot more than I do, basically. There's also another very exciting paper, which I'm quite keen on, but it's targeting C++ 26. And this is P2300. And this is about, like I said, this is about executors, which is a very deep concept. I mean, executors are to, function execution what allocators are to like memory allocation, right? So they basically decide what gets executed, where, when, and kind of how, and by what. So like I said, that's really quite interesting. And a lot of the coroutine, I mean, Guy, you probably know more than I do, but a lot of the coroutine work seems to be sort of heading, along those lines as well, basically. So, targeting C++ 26. Have a look at libunifex, which is a Facebook library which implements stud execution or stud executor. But that's very, very exciting stuff. So, yeah. Also, by the way, has everybody discovered, I just sort of wonder if everybody's discovered wg21.link? Yeah? I mean, obviously, Guy probably does nothing else, right? But, yeah? Everybody knows about this? All right, good. I mean, it's very useful, but if you just type into a browser wg21.link / and then the number of a paper, you get the paper. If you type wg21.link, the number of a paper / GitHub, you get the GitHub of, telling you the exact status of that paper. It's really very well organized. I mean, it's, incredible, really. So. Okay, conclusion. All right, so what we've got in C++ 20, coroutines provide a language capability. You can suspend and resume functions. So it's really very cool piece of machinery. They allow you to write asynchronous code in a way that's highly readable. And for me, I find it much easier to sort of debug coroutines. As I say, we spend most of our time reading this code. So it's really, sort of a major, it's a really good thing. Using user coroutines and user code, library support is improving. Personally, like I said, if your goal is to understand what's in C++ 20 coroutines, I would start with the references. I would start with, what's in Boost.Asio in particular. That's very good. But there are other libraries that are using coroutines. Have a look at CPP Coro. Persevere with the key references. Like I said, there is quite a lot of complexity, but it's quite rewarding, and you're getting insight into some really interesting stuff. So.